Hello students, in today's lecture we are going to study about the concept that electromagnetic waves are transverse in nature, or the electromagnetic waves propagate as transverse waves. What is meant by the word transverse? See, there are two types of waves: longitudinal waves and transverse waves. Transverse wave is a wave that oscillates perpendicularly to the direction of the wave's advance. That means in electromagnetic wave we have electric field vector, magnetic field vector traveling perpendicular to the velocity of light. Now transverse wave, it will be when these are perpendicular to each other. So we have to prove this point in today's lecture. Let us first quickly see what are waves. Waves are those which are traveling in the same x direction and they are not having any y or z component dependency, and their amplitude is same at all the points and in a plane perpendicular to direction of propagation of the wave. Now the plane wave solution of a plane harmonic electromagnetic wave propagating in an arbitrary direction of three-dimensional will be electric field intensity at position vector r and time t is equal to E naught, which is the complex magnitude of electric field, exponential e to the power of I k. K is wave propagation vector mathematically given by 2 pi by lambda. R position vector minus I omega t, and the magnetic field intensity B R position vector time t is equal to B naught, which is the complex magnitude of magnetic field into e to the power of I k dot r minus I omega t. K is propagation vector, wave propagation vector, omega is angular frequency, which is 2 pi mu, and t is time. All these small formulas are written here, you can see, and you don't need to write them in your copy. So E naught, B naught are complex magnitudes of electric and magnetic field. Now these physical fields are the real parts of E naught and B naught. K here is your propagation, wave propagation vector. K is wave propagation vector. K is wave propagation vector, and let us take n, which is a unit vector in a direction of propagation of the wave. Then we can write this k, which is wave propagation vector, is equal to k dot n, which is mathematically 2 pi by lambda, where lambda is wavelength and your unit propagation vector n. We can also write lambda in terms of frequency and velocity. There I have given the formula. C is equal to mu into lambda, where C is velocity, mu is frequency. So we can write this formula as 2 pi mu upon C, where C is equal to mu into lambda. And now we know that angular frequency omega is equal to 2 pi mu. So 2 pi mu becomes your angular frequency omega divided by velocity. And you can take the wave propagation vector n here if you want to. Now for free space where no charges are present, for free space where no charges are present, that means current density is equal to 0 at free space point. Then at free space we have Maxwell's first equation is del dot D equal to rho, where D is electric displacement vector. Now when charges are not there, we will write it as either D or E, because D is epsilon naught E. So del dot D is equal to 0, and Maxwell's second equation del dot B is 0. What we are now going to do is we will write del dot E in vector form, taking the x, y and z component, and instead of E we will write it down as E equal to E naught into e to the power of I k dot r minus I omega t. That is all. So now this simple expression is going to look a bit complicated. Nothing, we will just write del in terms of x, y, z and E in terms of the exponential factor, that is this complex amplitude. So let us begin. We are doing this so that we can prove that electromagnetic waves are transverse in nature. So now quickly we will prove it very easily. We will put the value of del and we will put the value of E in terms of E naught, and we will directly get the answer. So see, del dot E is equal to x, y, z component we are taking. So del by del x plus del by del y plus del upon del z and dot product of this E naught e to the power of I k dot r minus I omega t, right? Where E naught is complex amplitude. What is complex? Complex consists of real number and the complex part. Here this I is under root minus 1, and when you do its square it becomes minus 1. So we are just writing it down like this. Now what we will do is we will first simplify it for k dot r. Here this k dot r, we are going to simplify it for k dot r in the three directions, that is k dot r wave propagation vector k dot r into position vector can be written as in the three directions ax kx plus ay ky plus az kz, right? This dot of this position vector now we are going to open. So ax x, ay y plus az z. Okay, once again I am repeating. Now for the second step, in the first step del xyz, E in terms of your complex amplitude and exponential term has been written like this. Now in the next step, wave propagation vector in xyz direction and the position vector xyz direction, we are taking their dot product, right? So when we take dot product, a very simple vector formula, this is according to the vector analysis, ax into ax becomes 1, ay dot ay and az dot az equals to 1. So when we are going to open this, we are going to take the dot product. Ax into ax will become 1 and we will be left with kx into x here. Ax into ax is 1. dot ay dot is 1, az dot is 1, and this is dot product of the two. So when this reduces to 1, we are only left with kzx, kyy, kzz, right? So now we are going to we have used this formula of vector analysis here. So now this equation becomes k x plus k y plus k z, right? This is equal to k dot r. Now we will put this value of k dot r in this value of k dot r, we will put it here, right? And when we put this value here, what do we get? Del dot E. See, del dot E, that is electric field intensity. Del is xyz. So ax del by del x, ay del by del y, az del by del z, right? This dot, we are taking the electric field in the xyz direction. So it is ax e naught x. This is amplitude e naught x, amplitude of your electromagnetic field. Ay e naught y plus az e naught z, this much into e to the power of I, this value of k dot r, we are putting this here. So this becomes kxx, kyy plus kzz, right? This is the value of E dot r minus I omega t from here. Minus I omega t. So nothing, it is just looking a bit complex, that is all. Nothing new has been done, only k dot r has been written in terms of xyz using the formula ax dot ax equal to 1 equal to ay dot ay equal to az dot az. Now we will further simplify this expression. What we are going to do is, we will try to take all x terms at one place. What are we going to do in the next step? In our next step, we will take all x terms at one place, all y terms at one place, and all z terms at one place. How will we do it? Let us begin. We will take del by del x common outside, because now we are going to take the dot product of this, and e to the power will come in all the terms because it is outside. So now x, y, z terms. So let us begin. Our next step will be del by del x into e naught x e to the power of I kxx, kyy, kzz minus I omega t. Right? If you have understood it, very similarly your y and z terms will come. How has it come? See, del upon del x here, e naught ax dot ax, this ax dot ax has become 1. Ax dot ax is 1 vectors. So we were left with this much, and exponential term will be same for all. Similarly, I will write it for y. So this much plus del by del y, exactly similar. E naught y e to the power of I kxx plus kyy plus kzz minus I omega t, right? And next, last for z. So plus del by del z into e to the power of omega e naught z into e to the power of I kxx kyy kzz minus I omega t. So this equation is just looking a bit scary, that is all, and nothing else has been done. Once you write it for one term x, exactly similarly you write it for y and z. Formula used is ax is equal to 1, ay is equal to 1, az equal to 1, and we have just taken x, y and z separately. Now next step, we are going to differentiate this with respect to x, this with respect to y and this with respect to z. It will not be complicated at all. Very simple way I will tell you how we can reach our goal of proving that electromagnetic waves are transverse in nature. Now we have to differentiate this expression, right? We have to differentiate it. How are we going to differentiate? We know the formula d, here I have written d by d theta e to the power of I theta is equal to I e to the power of I theta, right? We will use this formula for differentiating it. We will differentiate how? Del E naught x upon del x is e to the power of I kxx is equal to I kx into E naught x e to the power of, now here this will all be common, so kxx plus kyy plus kzz, right? This is what we will get if we differentiate this with respect to x. That means an additional term I kx comes for x, I ky will come for y and I kz will come for z. So we will put these additional terms, and what are we going to get the equation as out here? This will now be equal to E naught x I k x plus E naught y I k y plus E naught z I k z e to the power of I kxx plus kyy plus kzz minus I omega t, right? Now how are we going to simplify this further? What we will do is, we will take I. See, I is there. This is the complex part in all the three. We will take it common. We will take out this I common from here, and we can write this expression as I into E naught x plus E naught y I into E naught x kx plus E naught y ky plus E naught z kz, right? We have only taken I common, rest e to the power will be the same here. It will be e to the power of I kxx plus kyy plus kzz minus I omega t, right? Now what are we going to do? This is the value of del dot E. This we are just going to play a very small trick. We can write it down. We can take, see, we know that ax dot ax is equal to 1, ay dot ay is equal to 1 and az dot az is equal to 1. So if I multiply this by ax and I multiply by ax and again I write the vector factor. It will come back to a dot ax equal to 1. So this very small trick we will play here. A very small trick we are going to play here. How? See, we are going to write this expression as I ax kx plus ay ky plus az kz dot ax e naught x plus ay e naught y plus az e naught z, right? And e to the power of I. Now I can write this down as k dot r also. We have already found k dot r in this lecture itself. Minus I omega t. What did we do? Nothing new. Just we have written this like this. When you will multiply this with this, ax dot ax will come out as 1. You will be left with e naught kx. Nothing has been done, just a way of writing it down so that we can find a simpler way of proving that they are transverse in nature. Now, what is this ax kx plus ay ky plus az kz? What is this value? We have derived it earlier also, that simply now we are going to write it down like this. So this becomes equal to I k dot e naught e to the power of I k dot r minus I omega t, which is equal to I into k dot e. So that we could just write it like this. We played this trick. That is all what we have done. Simple. This becomes I dot k and e naught is this much, e naught e to the power of I, which has been written as the exponential form here. Here where e is equal to e naught e to the power of I k dot r minus I omega t. Now we can use the del symbol and write del dot e is equal to I k dot e. We did it all these things purposely so that we could write k dot e. K is wave propagation vector k, which is equal to 2 pi by lambda. Now for free space there are no charges present. That means charge density is 0 in free space. So free space, there are no charges present. Charge density is 0 out there. Your Maxwell's first equation becomes del dot E equal to 0. And so del dot E will become 0 when k dot E will be 0. That means k dot E is 0. Necessary condition for, and similarly for the magnetic field. Similarly for your magnetic field also, del dot B will be 0 when k dot B is equal to 0. Hence, necessary condition for your free space is, for free space to occur is k dot B should be equal to 0 and k dot E should be equal to 0. What does this prove? This conclusion indicates that the electric and magnetic fields are perpendicular to each other. B and E are perpendicular to each other, and perpendicular to the direction of propagation vector k. That means we have proved that they are transverse in nature because EB is coming perpendicular to each other and perpendicular to the propagation vector k. That means electromagnetic waves are transverse in nature. Thank you.